Okay, and our third speaker is Roger Prince. Dr. Prince is a Senior Research Associate with ExxonMobil Biomedical Sciences in New Jersey and has worked on a number of aspects of environmental and bioprocessing microbiology, both during his career with ExxonMobil and prior to them. He is, interestingly, doing some work on algal biofuels in ExxonMobil's alliance with Synthetic Genomics Incorporated. Has also been on faculty at the University of California at Berkeley and the University of Pennsylvania. He's published more than 300 papers and chapters in the literature and was awarded the Stanford Farrell W. Lytle Prize for contributions to synchrotron spectroscopy in 2000. Thank you so much for being with us this morning, Dr. Prince.
Good morning, and thank you very much. I'd like to give you a sort of industry perspective. And what I'd like to do first is emphasize the other speakers have talked somewhat about the scale of the amount of energy that we use. But at least from our point of view, the scale of energy use really puts biofuels into an interesting perspective. So you've heard this before from the other speakers. We expect the OECD's population to stay more or less constant, but GDP to carry on rising. And you might expect that would mean there'll be an increase in consumption of energy, but the expectation is that efficiencies will mean that the OECD will probably not use much more energy over the next 30, 40, 50 years, while the rest of the world will grow substantially, both in population and in GDP and in energy consumption, but that there will be huge amounts of energy saved because of the efficiencies that are coming into the market. And there is a very diverse mix of things that contribute to the energy that we use, but it is a staggeringly huge amount. This obviously is the total amount of energy, and then the renewables are then expanded here into this category, and then from there the biofuels are expanded out into this category. You'll notice that this biomass it seems very large. It is very large. This, from our point of view, is the evil biomass. This is the biomass that people use for cooking in the form of, say, animal dung or very green vegetation. There's a really strong drive, both from the consumers, but also from NGOs and governments, to try and persuade people to actually stop using that biomass. So there will actually be, we hope, a lower consumption of total biomass. You can see that massively dominates the amount of biofuels that are used. So there's a huge amount of biomass is used for energy in the world. Only a tiny fraction of it gets used for biofuels. And that stuff that is used as biomass for cooking, it would really be a good thing if we somehow move to something different. Obviously, the energy use has evolved. The source of energy has evolved over time. One of the other things that people forget when there's this debate about no food for fuel, we should remember that back in the 1800s, the average American farm used at least a third of its production to fuel the animals that provided the motive power for that farm. So this idea that you can actually produce food without having to produce motive power is a very recent phenomenon, courtesy of the internal combustion engine. And in the past, people had to both grow their energy and their food. You can see how small the area of renewables is in this scheme. The amount of energy that we use is so staggering that even though we use quite a lot of renewables, it's tiny on the real scale of things. Another issue that I think is not widely understood is just how much energy we use on an individual basis. This shows you here the daily energy use in BTUs per person. I'm sorry the oil industry is relentlessly non-metric, right? Occasionally I'll slip in a hectare or something, but we'll stick with BTUs for a bit. But to put it into perspective, right? A human consumes about 2,000 kilocalories a day, which is about 8,000 BTU. And again, if you think back to 1800, the average person, that's what they had to work with, right? If they went to chop wood, they were using that 8,000 BTU as an investment to chop wood, to get wood. Today, we on average use 740,000 BTUs per person. It's just a staggering increase in energy consumption, which of course allows our modern lifestyle. It's just so radically different. But you can see here the red is the energy that's sort of hidden from us. It's the energy that is used to make all the bits and pieces that we see, to put down roads, to The actual personal energy use that we would recognize using is the dark blue, and the pale blue is the amount we use in personal vehicles. And again, you can see how North America is radically different from the rest of the world, even from Europe. And energy use will grow despite the, and it's included in those predictions that I've shown there, because it's another one of these things that people don't recognize, is that approximately a quarter of the world's population doesn't yet have electricity. And something like a third of them don't have useful modern cooking and heating. And those people all are going to want to have some energy use. So there is a tremendous suction for more energy use. While we're trying to be more efficient, you saw from that last graph, we have a long way to be more efficient from. There's also a lot of people who have a long way to grow. So there clearly is a nascent demand for fuels, and obviously biofuels fit the public's view of what that should be. So just to, again, put it in perspective, the industry and indeed all the agencies imagine that we are going to get more and more efficient. This is a projection of what we'll need to do if we, from MIT, if we're going to try and keep CO2 levels at a particular level there, 550 ppm. The red line is business as usual, which is where we aren't allowed to be, where we can't be to get to 550 ppm. And you can see the expected decline in fossil fuels and then that increase in efficiency and demand reduction, those things. But there's still that big chunk that's not colored here, which is, well, we hope it's bioenergy, you know, we hope it's nuclear, we hope it's something. And of course, again, there is tremendous public support for bioenergy. I'm afraid it's rather more optimistic than our view. The big issue, and it's been talked a bit already today, is that the Earth does do a wonderful job at harvesting sunlight and making things. Right? The net primary productivity of the Earth is staggeringly large. We've made the photosynthesis has put this world wonderfully out of equilibrium to allow us to be here, to live here with all the oxygen that's around. And the total net productivity, as you see, is 56 gigatons per year. It's a staggeringly huge number. It turns out that we already use about a third of it. I mean, it's just amazing the influence of humans on the modern globe. So any increase in using that stuff that's out there will have to be very efficient, and of course it will take it from something else. There is just this net primary productivity. The only slight optimistic view is that perhaps we could grow crops where today there are no crops, but that's, well, we have to hope for that, right? And we have to hope it'll be efficient. But we already do an amazingly good job at harvesting the natural world, and it'll be very hard for us to harvest a lot more without displacing every orangutan and every zebra. So the first generation biofuels, you know what they are, right? In the two that we use are ethanol and biodiesel. In the US, we make ethanol from sugar and starch, and it can also be made from cassava and wheat and sugar beet in the tropics. And of course, the really big gorilla is the sugarcane in Brazil. And sugarcane is really quite efficient, as we'll get to. And then biodiesel, which takes the vegetable oils that otherwise are wonderfully valuable for cooking. And in the US, it's mainly from soybean. As a beekeeper, I can say that soybeans are disappointing. They don't make any honey. And in Canada, in Europe, they use rapeseed, and rapeseed makes a quite delicious honey. So there are hopeful, optimistic things that some biofuels have nice side effects. The trouble is they are dreadfully inefficient. Clearly, I don't expect you to read this slide, but you can calculate how efficient the system of growing ethanol, either from sugarcane in Brazil or from corn in Iowa, and you can calculate the efficiency of how much sun comes in and how much goes out as a nice liquid ethanol. And the answer is it's very disappointing, right? In Brazil, it's 0.14%. In the US, it's 0.03%. So biofuels are not a very good solar fuel, but that's what they have to be. We have to be harvesting the sun if we're not going to use stuff that was harvested millions of years ago. So there are real issues here around biofuels and whether they can be efficient enough to be useful on a significant scale. It's generally agreed that in the US, we make about a 30% energy profit when we make ethanol. So that means that you need to produce 4 liters of ethanol to export 1 and have a completely self-contained energy system, which of course means that you're doomed. But the other thing we need to remember from ethanol, and those of us who are carnivores, we actually benefit from this, you get a rough equal weight of ethanol and animal food when you convert corn into ethanol. That's very important both for the economics. It's also important in that the dried distillers' grains can't be stored very long, so they have to be put through the animals quite quickly, and so that keeps the price of meat gratifyingly low. On the other hand, if you want more ethanol, that does mean you're going to have to commit to eating meat at every meal, because there's going to be just too much animal feed otherwise. The other important thing that is known but not usually talked about is that you could define corn ethanol as mining. We lose about 4 kilograms of soil for every liter of ethanol that's made in the Midwest. It all goes out down the Mississippi. It's an interesting question as to how long one can continue doing that. And of course, there are real efforts to go to no-till farming and to cut that number, but those are the current USDA numbers. On the bright side, one of the nice things about ethanol production is that it makes pure carbon dioxide. And today that is all captured. Usually it's sold, say, to Coca-Cola and used to carbonate sodas. But if you wanted to do carbon capture, it's the best place to get CO2 because it doesn't require any purification. The off-gases from a fermenter are pure CO2. So you can readily compress them, and you could bury them underground, and you would have carbon sequestration. And indeed, there's a pilot plant going on at an Arthur Daniels Midland distillery in Decatur. But if you were to do that, in fact, in Brazil, the efficiency is such that ethanol would become a CO2 negative fuel. That if you were to capture every sugar, right, the 6 carbons in every sugar becomes two carbon ethanols and 2 carbon dioxides. If you were to put those 2 carbon dioxides down underground and bury them, which you can do, as I said, it's being shown in the pilot project, then actually as you were to continue to consume that ethanol, you would actually be removing CO2 from the atmosphere. On the other hand, we still are faced with the scale at which we could do this. Biodiesel yields much less than corn, about 50 to 60 gallons per acre instead of many-fold more. And again, the press cake goes to animal feed. Again, sugarcane is a different biofuel because the sugar gets consumed to make ethanol and the rest of the plant is burnt. There are no real co-products. The burnt fuel, the burnt gas, fuels the system, does the distillation, and can drive turbines, and some distilleries export electricity. There isn't a food component in the byproducts. Both the US fuels, corn and soy, both have an animal food component in the economics. And they are an important part of the economics. Already these fuels are expensive, as you heard, but part of the economics comes from the fact that there is a valuable byproduct. Again, if the production increases by very much, the value of the byproduct will decrease. Again, there are serious problems of soil erosion with producing biodiesel. Now, there are other things you can make instead of ethanol. The first generation, of course, are the classical ethanol fermentations, but there are other fermentations you can do. You can make acetone and butanol. There are several companies trying to commercialize butanol right now, isobutanol, either using bacteria or yeasts. And there are these microaerobic systems where algae and yeasts, algae growing in the dark, convert sugars into oils. And these are important, for example, in baby formula. And there's a possibility of making other molecules like farnesene and farnesane, which are branched small alkanes, in engineering yeasts. The trouble is that all of these require a reasonable purity sugar. And corn syrup works well, but it's expensive, and the yields are such that these are not yet commercially valuable. Obviously, everyone would like to go to converting cellulose into sugars into these products. But that's turning out to be really quite a challenge, as you've heard. The amount of ethanol produced from cellulosic fermentations is very small, and the amount actually sold to the consumer is very small. One of the problems is that although you can readily grow cellulose, to separate the cellulose from the lignin that comes with it in the plant is a challenge, and it seems to be different for every different plant. In other words, if you make a plant that can more or less efficiently deal with corn stover, you can't tomorrow take a load of wheat straw. You can't tomorrow take a load of rice straw. It's looking as if these processes are going to have to be very crop specific, which makes the whole system rather more tenuous. It doesn't have a fungibility to it. There are lots of things that go on there. For example, cellulose has roughly equimolar pentoses, 5 carbon sugars, and many organisms can't grow on those. So there's a lot of development of strains, a lot of genetic engineering. I think we're still quite a long way away from seeing any realistic use of cellulosic feed sources. And one of the big challenges is that all the economics for this imagine that farmers will be willing to sell cellulosic biomass for the order of $40, $50 a ton. Well, today they can get $200 a ton for hay. So if I was a farmer, I don't think I'd be changing over, and I'm not sure many of them will. So there are many bioenergy pathways emerging. Obviously, a very simple one that's used certainly in Scandinavia is burning biomass to make electricity, and that does work. It works effectively. I've talked about the anaerobic conversions. Another anaerobic conversion is actually to first gasify the biomass and take the methane and carbon monoxide that you get out of there, depending on how you gasify it, and converting that by a microbial process into liquid fuels. And people have started working on that, but right now the price of natural gas is so low that they're moving from using biogas to moving back to natural gas. You can also imagine converting the gas from gasification of biomass into methanol and converting methanol into gasoline. That's certainly been done on a commercial scale, but it's not practiced today. I've talked a little bit about cellulosic ethanol, about pretreatments, the hydrolysis, that's the big challenge, and then separating the lignin from the cellulose, and then fermenting it into ethanol and perhaps other things like butanol, other alcohols. And then finally, probably furthest on the horizon, but has some at least appealing benefits on paper, are growing algae. Algae, of course, grow well. They are photosynthetic. And when you think about it, they don't waste any time with wine, women, or song, right? Most algae don't undergo a sexual cycle, and they just grow to make more algae. The nice thing about algae are that they grow all year round, and you can imagine that you could always adjust their concentration so they're always very efficient growers, users of sunlight. When you think about corn, for example, right now corn is the world's worst bioconverter, right? 0% efficient growth going on now in Iowa. Every photon is being absorbed by the soil or the snow, but none of it's doing any useful work for us. You can imagine with algae, since you're going to have to add carbon dioxide, which is a big problem for algae, you're going to have waste heat, so you should be able to grow algae year-round. So that should get you a far more productive per area system. But it's a very long, we are actually working on it, but there's a long way to go before this is likely to be useful. One of the challenges is to persuade the algae to make oil rather than to make more algae. So, since we are in Washington, D.C., oh my goodness, the colors aren't. Oh, I have to push the button several times. I didn't realize it was so clever. This is showing you the size, what we imagine are the efficiencies of aerial efficiencies of growth, in this case to produce approximately 0.1% of total US road transportation fuels. So we're saying, well, we'll just call a gallon of fuel a gallon of fuel. We understand that soybeans make diesel and corn makes ethanol. And so you can get an idea roughly from these rectangles that are appearing here. Sugarcane is significantly more efficient than corn in producing ethanol. Unfortunately, it only grows in very small parts of the US, down south. Palm, of course, doesn't grow at all here, but it's even more efficient. And then we're hoping, with some research, that perhaps algae could be that much more efficient than corn and soybean on an aerial basis. But that issue of efficiency is a long way from being sorted out. These are back-of-the-envelope calculations. So at the end of the day, the question for biofuels is whether they can be produced on a large enough scale to be of any real importance to the world. We use these staggering amounts of energy, right? 45 million barrels of oil equivalent per day. It's going to even grow a bit further. on the whole world. And these numbers are just so staggering that it's a real challenge to imagine biofuels having a big impact, but that is the challenge. And as you do produce them, can you do it with an acceptable environmental impact? As I've said, naysayers could compare current biofuels with mining, right? We lose more soil than we gain in fuel from current farming practices. So in the long run, whether we can do this is a real challenge, and I don't think the answers are at all clear yet. Thank you very much.